Okay, so so if you are a mathematician and work on the east coast of the US, and I ask you what is true, you say what is provable is true. Then you visit the west and you ask to Tarski or others, so Pravis, for example, on the east, what is true? He says what the model tells you is true, and poorly computer scientists go from east to west, and I think it's bad because we already have the model, and so we should go west to east from the model to proofs. And that's what I will do, and how you do it this way. First, you define the natural relational semantics, because I consider only transformational semantics input-output. You must be structural, otherwise it's not funny. You can use rules, and I will give you a fixed point. Okay. Then you define an abstraction, alpha, of the collecting semantics, which is the most precise hyperproperty that defines the theory of the logic that you want. And the theory is a set of true formula. When you have this, you calculate the theory in structural fixed point form by fixed point abstraction. Why fixed point form? Because when you have the fixed point form, Mr. Peter Axel showed how to get the rules. Okay, plus you have this fixed point induction, I will explain why. And I take two trivial examples, which is OR logic and incorrectness logic, and they are not even in the paper because they are too trivial. But for a talk, for a talk, it's not so bad to be trivial. Okay, so what is the general idea? I apply it. You take OR logic, you take the strongest postcondition of the collecting semantics, okay? Then you have no consequence rule, so you had an approximation with the consequence rule, okay, you got it. Then you over-approximate have an approximation of fixed point, as we will see, and then you use Axel correspondence and you get the OR logic. I will show. Then if you are under-approximating, you replace over by under, and you do exactly the same thing, which explains that their two systems are related. So let's do it. I start with this small language, which is classical. I don't handle this in my talk. I don't handle nontermination, so I have only states and an angelic semantics which says if you start in this state, you may reach this one. Then I have to formalize this, so I use judgment. The first one say if you start in state X, sigma, you execute S, you might reach final state sigma prime. And to do that for the Y, I have another rule which says if I start in sigma, I make 0 or more iteration, I might terminate and reach sigma prime. So here are the rules. You see, for the while, if I am in state sigma, I do 0 iteration, I am in state sigma. No one disagree, okay? Then if you are in state sigma, the test is true. You execute the body, it may terminate. Then you do n more iteration. Then from sigma, you can do n plus 1 iteration, sigma prime. And if you can reach a state for which the test is true, false, excuse me, you have terminated. And so Mr. Axel, I will show you later, tell you this is the same as this fixed point, where you say you have the least fixed point that give you the relation between initial and n iteration, and then you don't terminate, you terminate here, and the relations say ID is just I am there, I stay there, and the next one say I do one iteration, and then I get n plus 1 iterations. We'll see why. Okay. And then we come to Mr. Axel. He says, if you have rules in some universe, the precondition must be finite because you have proofs. The postcondition is an element of the universe, and if P is empty, you say that it is an axiom. Then you have a deductive system, which is maybe infinitely many rules with a premise and a conclusion. And now these define a subset of the universe. How? The first thing is you consider the provable things, and the proof is a sequence of terms, so that any one is a conclusion of some rules, so that you have proof before the premise, and then you take the next term to be the conclusion. That's the classical stuff in math. You prove by doing little steps of induction. And he said also it is the least fixed point of the consequence operator. And the consequence operator is this one for this rule. You have hypothesis X, and you derive all the possible conclusions that you can derive from X using any rule. And what is interesting is that if you have any fixed point with a set order, there is a deductive system so that this fixed point for this deductive system is this one, which means if I have a fixed point, I can express rules. That's why I was saying express the theory with rules, because applying this, I get the rules here. So for the logic, what we do, we start from the collecting semantics, which is the singleton of the strongest property of the semantics. Then I do an abstraction to get the semantics. It looks ridiculous, but here you have all hyper properties, so it's interesting. Then I have a transformer, which is pose, right image. Then I have representation of a function by its graph. Then I introduce over or under approximation, and I am finished. I've got the logic. So the first abstraction was a Galois connection between hyper properties and properties, or trace properties. Sometimes you just take the union. So you take the union of all traces, and you have lost information. You, for example, you cannot no longer define dependencies or things like that. Then the post image is trivial. It's another Galois connection between a relation and a transformer, and it's just a post image. That is, you take all state in P and then apply the relation and look where you arrive. And the last isomorphism is you encode the function by a functional relation. That is, for each argument, you remember the value of the function for this argument. I cannot make more trivial. It's completely trivial. And so now we have a logic. I take the strongest postcondition logic to be the abstraction that we have defined. So for each precondition, it gives you the strongest postcondition. And you use some notation, which is not really interesting. And then I want to have this in fixed point form for my semantics. So I have this theorem, POPL 79, which says if you have a Galois connection between complete lattices, you have a concrete and an abstract function, and they commute, then the image of the least concrete fixed point is exactly the abstract fixed point. So to apply it, I say this is the semantics, this is the alpha that we have defined, and now I will have the theory of the logic in fixed point form. Then I apply Axel, and I am done, or almost done. Okay, so I do it, and I get this. So for the while, you start with P, and what is true, the strongest invariant, if you want, is P, or after one iteration, by the fixed point, after two iterations, three, the union of all this is the strongest invariant, then I must exit, and that's it. So Mr. Axel the abstraction, move to this, and then Mr. Axel tell me, you are finished, you have got a proof rules. He doesn't want to go to next. But okay, so this one is my exercise. You see, I have the definition, few properties of pose. I prove commutation, fixed point abstraction. I get the result. You see. Okay, so now we are missing implication. We have no consequence rule, so we are always speaking of the strongest invariant, and no one wants to do that. So I introduce this order. I have a pair, so X is precondition, Y is postcondition, and I compare the two. And let's go for OR. For OR, I take post of these two orders. And if you say here, if this is a valid OR triple, you under-approximate the precondition, you over-approximate the postcondition, and this is a valid OR triple. You agree? You agree? Oh, okay. You are following at least. So, so under, we said it's a dual. So I take the dual, you see, blah, 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 and I get, this is an incorrectness triple. I take an over-approximation of P prime, an under-approximation of Q, and this is another OR triple. Okay, so now we have done, we apply the Axel correspondence, and you see that we will have a common part between OR and IL, and the only difference will be the consequence rule. Okay? And it's good, but you see, it's sound, it's complete, but it's not really usable because my method given by Axel say prove the strongest invariant and then make the approximation. No one does that. But for a mathematician, he's finished, he can retire. It's, so what we miss is fixed point induction. Because we don't handle fixed point or iteration the way I said. You don't look the most precise and then approximate. You just approximate. So the first one for OR will be Park fixed point induction. It's an immediate consequence from Tarski theorem. It says you have a increasing function on a complete lattice. You want to prove that P is over the least fixed point. What you do, you find an inductive invariant, which is more precise. And by Tarski, this implies that, and the other way, the I, you take each fixed point, and it works. Okay, so now for the incorrectness logic, you want to under-approximate the fixed point. Where is this written? Okay. Yes, it's written here. You want to under-approximate, so you take the transfinite iteration, and you go always under the transfinite iteration, and so because you are under some iteration of the transfinite iteration that are under the iteration for the least fixed point, you are in the least fixed point, and this is complete because X, you just take the iteration of the least fixed point. Okay, so you see that now we have two different things because for OR it's one fixed point induction and for IL it's another one. Okay, so you can calculate, you see I calculate the theory, and here I have applied for OR logic the Park induction, and so I get the rules by because now it's an axiom, so I get this rule trivially, and I made it, you see, I start from the definition of the theory, I use a fixed point induction, I am happy, and I say, Mr. Axel, tell me that for an axiom is completely trivial, and because I am not really a serious mathematician, I put the side condition as a precondition, so I mix the rule and the structural induction, but who cares, huh? So so I was surprised because I discovered something in our logic. You see, 47 years later, you discover, it's even more, it's almost 50 years. So what I discovered, if you do host of equal and less than, you have the same theory, which means the consequence rule, let's go directly to, this rule is useless except for iteration. Because my fixed point induction, I initially P is less than the invariant and so on. And so it was a surprise. Yeah. So now for IL, I take the definition here of the theory, I apply my little theorem, and I get this. So this is a rule of Peter, and to get it, you see, I compute, I use the theorem, it's equality everywhere. Here I have got an axiom, and so I apply Mr. Axel, and that's it. Okay? So simple, huh? So there is more in the paper, because otherwise, if you speak about trivialities, your paper is rejected. And if it's also too complicated, it's also rejected. So there is a balance here, not easy to find. And I almost, I was lucky. So I take a B-inductive relational semantics. It means for finite computation, I use a least fixed point. And for non-termination, I use the greatest one. And some guys say co-induction is better. You have one way of induction for the two, but then you cannot apply my fixed point approximation theorem, and so you are in bad shape. Second, what is the difference? There are more abstractions, so I have more than 100 logic if you combine all possibilities. Then so some of them, there is a taxonomy, you can put them. So we have seen these 2 points and this one. Okay, so that's not so bad. The others you can derive yourself. Then I need many fixed point inductions, smaller or greater than the least or fixed point or greatest fixed point. Intersection is not empty, intersection is empty, and things like that. Depending on what you prove, you need many different fixed point induction. And to be serious, I developed in the paper 2 logic. So here is an application. I have factorial, and my logic, I can say if n is positive, f will be factorial. If it's negative, it does not terminate. You cannot prove that with all logic. This you can prove, but this you have no guarantee of termination. If you take the termination of logic of Mana-Apnueli or Abt-Plotkin or this, you cannot prove this because it's only work if it's totally correct. And then I have another one because Peter, who is there, you see, he promised to ask a difficult question. So I am waiting for the question. So he says, if your analyzer produces an alarm, you can prove it is a false alarm with incorrectness logic. And this is an example where you cannot. So, so I have my factorial. I say n is integer, f is 1, and 47 years ago, I showed how to prove that you know nothing at the end, which was a great result. Huh? But you can specify that it is positive. Factorial is positive. And now it's a false alarm because my analysis will say it can be any value f. So why is it a false alarm? You cannot prove it by incorrectness logic because it is a false alarm because it does not terminate in that case. And so in the concrete, it does not terminate, so it never reaches point with negative. And in the abstract, it can, and this is the origin of the false alarm. Okay? So, well, okay, that's it. And this slide is the last one I gave for Peter, so I repeat it. So incorrectness logic for me naively was incorrect is not correct. So not correct is not or triples. And surprisingly, it is implied by incorrectness logic, but it's not complete. and you must, in fact, invent some R for which it works. And this R is the part of Q which is wrong. There is also a possible part of Q which is correct. So you have to eliminate it and then show that the intersection is not empty. But you see, this formula is not a formula of incorrectness logic. It's some other stuff. And in fact, you can prove it is enough to have one state which is wrong, to be wrong. And if you do that, you can develop the logic, and what you get, a formalization of debugging. So it's very funny. Here is a formalization of debugging, which is interpreted as a logic. And so you see debugging is a formal method. Now. So if you remember nothing of this talk, which I think most of you will do, just remember a transformational logic is an abstract interpretation of a semantics. If this is too hard to remember, just anything is an abstraction of a semantics, and that's okay. Thank you. Okay, so I am waiting for Peter's question. You see, he's ready. He has had 1 week to think about it. I am completely anxious, and so I have to listen carefully.
The title of the paper had you
speak too fast.
You were calculating, in some sense, the title of the paper, the logics.
Yes.
But there's one point that I didn't see the calculation. So you used, I think it was called Park induction for the under-approximate logic, and no, Park was for over, and fixed point induction was for under.
Yeah.
I think you could. I have several questions there. I think you could have used fixed point induction for both. Is that correct?
Both are fixed point induction, but they are different. One is to over approximate, the other is to under approximate. But if you take the dual, then you over approximate and under approximate greatest fixed point.
I know.
And my semantics are not greatest
Correct,
fixed point. And that's why it would not work to have a greatest fixed point semantic, because the abstraction doesn't work.
We agree. This is why the theories are not really dual. But what I'm getting at is that you used, in the over-approximate case,
yes.
I can just choose one loop invariant. And there's various jargons for this. It's like some kind of invariants are complete. Whereas in the under-approximate case, I need to have something like a variant function. So I list many of them.
Yes,
right?
You have an index invariant.
A proof rule like that is sound in the over-approximate case, but we don't need it because of the completeness of inductive invariance. So what I'm wondering is, when you do this calculation, when I was thinking about these, I had to I don't really need that strong induction rule for Hoare, but I need it for the under. So this was all quite puzzling to me. Now, can you calculate that, or do you get similarly puzzled and now you have to invent?
No, at some point you have to have a minimum of intelligence. And that's unfortunate. That is, you cannot push the button and say, give me the logic. You have to say more. You have to say what is the theory, so this is not so difficult. But I think the induction is, which induction you are going to use is difficult. And if you do static analysis, doing the Galois connection abstraction is easy. It's a lot of code. But what is difficult is fixed point induction, which is widening, narrowing, and all these
I have one further question. So the induction rule for the under-approximate logic, or the loop rule, looks very much like the loop rules of Pinelli, the total correctness proof rules. Do they have the same induction principle when viewed from the lens of what you're talking about? They look the same syntactically.
What you said, excuse me. I am dur de la feuille, as we say in France. I don't know if this in English. Dur de la feuille, you know what it means? No. Okay. And the two leaves, in fact. So can you repeat that?
Are the total correctness proof rules and the under-approximate proof rules for loops, are they the same induction principles?
They are using the same principle. but you can express it in different ways, and you can introduce, because it's total correctness, you see, you have a property which is more precise than the general case. And then you can introduce well-founded things and so on. So it's a more refined instance of the induction principle. But it's even in correctness logic, I can translate this into a well-founded thing. That is, it must reach under after finitely many steps. That might not be complete, but with hypothesis on the language, it is. So, whereas total correctness forces you infinite steps, infinitely many steps. If you have unbounded determinism, non-determinism here, you might have to go to a transfinite induction. But if it's totally correct, you don't have. So you have a more precise induction principle, but one is the subcase of the other.
My last thing I'd like to say is thank you. And you were wrong in one place. I think many in the audience will remember a lot of things from this talk. So thank you.
Thank you.
All right.
Most questions, so maybe we can stop there. No?
Yes, I think we need to call it off because of
I survived the Peter's question, so I can do it on any other. But I take question if you want afterwards.
Thanks for the patience.